So before we can do energy diagrams, I need to go over some terms. Some of these will just be review, no big deal. Others will be specific to doing energy diagrams. So this all has to do with enthalpy. We'll get into more depth with that. But first of all, we know our reaction has our reactants on the left, our products on the right. You have the terms there. Activated complex is what we refer to when we talk about an intermediate phase when molecules are breaking bonds and starting to form new bonds. So in other words, it's when these start breaking up and then they gradually start combining to turn into your products. So intermediate. Activation energy is the amount of energy needed to increase collisions and cause reactions to occur. If you just have the items, that doesn't mean that they're going to react. So let's say that we take two powdered substances and put them in a beaker. They're not going to react. However, if you dissolve them both in water, the fact that they're in water allows them to move around, which then causes those collisions and can make that reaction occur. So sometimes activation energy is just as simple as making them both, like both of your reactants, soluble. Exothermic gives off heat or light, and it has lower potential energy after the reaction has occurred. Endothermic stores energy in bonds and has higher potential energy after the reaction has occurred. In order for a reaction to occur, they must have energy, and the particles must orient properly. So you might have particles that could react, but if they're not colliding in the correct manner, then they may not end up reacting. Here we have an image of an exothermic and an endothermic reaction. This is what an energy diagram is going to look like. You'll have your reactants. This would be the value of energy that the reactants have, whatever the measurement is on the potential energy here. And then, in this case, the activation energy is the energy needed to get it to get over the hump, okay? So this value of energy has to be put in order for the reaction to occur and then turn to the products. So this is your activation energy, and it's your activated complex. Sorry, couldn't think of the word. Okay, your products down here have less energy than the reactants. You can see that because they're lower on the potential energy scale. And your reaction progress, this is basically time. So they start as reactants, and then they gradually change to the products. Here's an endothermic reaction. So this one's storing energy. The reactants are starting with a lower amount of energy. You have a whole bunch of activation energy that has to go into it. Activated complex would be up here at the top. And then once you get that energy, it's going to go ahead and come down to the products, and the energy is going to be at this new level, which is higher than what it was. So we've got energy absorbed, and that's our endothermic. Here we have another scale. So these would be your reactants. This is the value of energy for the reactants. Here would be, for letter B, that's going to be your activation energy. So the amount of energy to go from the reactants to the top of the peak. C is going to be your value of energy for that activated complex that's up here at the top when it's in that intermediate phase. And then we have our energy here, which represents the energy of the products. Collision theory is something else we can kind of talk about, and it believes that reactions happen when molecules collide with each other. It requires energy, and it requires correct orientation. 4 factors can impact collisions. Concentration. So the more particles there are, the more likely they are to collide. The less particles, the less likely they are to collide. So the more concentration, the more collisions. The less concentration, less collisions. Temperature. Temperature has to do with how fast the particles are moving. The warmer it is, the faster they're moving, which means there's more of a chance of colliding. Surface area, how big they are. So if they're bigger, they're going to be more apt to hit something versus if they're really small, they might go right past what they're trying to hit. Catalysts can lower activation energy. So that can actually If we want to talk about catalysts, catalysts are going to lessen the activation energy. So the letter B is the activation energy needed to cause this reaction to occur. A catalyst would actually cause this to be a lower value. So if I go ahead and mark this in, and you can mark this in on your notes too. So my activation here would just be the value from the reactants up to this new peak. And that would be where my new activated complex would be, because the enzyme is going to help make that reaction occur faster. Typically, we talked about enzymes in biology. We talked about catalysts a little bit, but a catalyst is like an enzyme. A catalyst is actually going to make an intermediate phase in which the reactants will make a different product and then go to the final product faster. So that's typically how catalysts work. All right, change in H is going to be the difference between the energy of the reactants and the products. If it increases, then it's positive. If it decreases, then it's negative. So that determines whether it's going to be endothermic or exothermic. So this one, our reactants are up or higher. Our change in H is going to be negative because it's going down. So that would be an exothermic reaction. So change in H is the difference between the reactants and the products. And then heat of reaction, what happens if it's a reverse reaction? So sometimes it will ask questions about the reverse reaction. Reverse reaction is just going to be going from the products to the reactants. So you're going to look at the reaction in the opposite direction. So if we were talking about it that way, the reverse reaction, we would now call these the reactants, these the products. We would need a lot more activation energy if we go in the reverse reaction. And then this would be endothermic instead of exothermic. So what is the activation energy for the forward reaction here? That's going to be A. And for the reverse reaction, our activation energy is going to be B. What is the change in H for the forward reaction? Change in H would be your reactants, the difference between that and the products. So the change in H will be a positive value because it'll end up being 200. For the reverse reaction, you're going from high level to a low level, so that it would be a negative 200. And then what is the energy of the activated complex? That's going to be just whatever this value is at the top of the peak. It's going to be the 400.